Bjarne Stroustrup, the creator of C++, once said that code should be elegant and efficient. The logic should be straightforward, doing exactly one thing well, leaving no place for bugs to hide. But even the most meticulously structured logic eventually faces the real world, and out there, things get messy. Programs behave abnormally. Sometimes they refuse to run at all. The most basic way a script fails is through a syntax error. This happens when the strict grammatical rules of Python are broken, like missing a parenthesis or misspelling a keyword. These parsing errors are actually incredibly helpful. The Python interpreter simply refuses to execute the program until you go back, find the typo, and fix it. You are protected from running broken instructions. The real danger lies in code that is syntactically perfect but runs into an impossible situation during execution. For example, your script might try to open a file that a user deleted, or it might attempt to divide a number by 0. As we can see in this shell output, dividing 50 by 0 triggers a very specific response from Python. When this happens, an exception is raised. The normal, step-by-step execution of your script is immediately disrupted. Without a safety net, the entire program crashes to a halt. We can never predict every bad input, hardware glitch, or missing file. Our challenge is to engineer a system that can manage these inevitable errors behind the scenes, keeping the program alive and the user experience intact. To help us manage these failures, Python comes with an extensive standard library of built-in exceptions. You can think of them as highly specific alarms, each wired to detect a different type of failure. Looking further down the output, we see another common alarm. A type error rings here because an operator was supplied with an incorrect data type, in this case, trying to add a numeric integer directly to a text string. In the exact fraction of a second that an error occurs, Python creates an exception object. This is a package of data containing vital metadata about the crash, including the specific type of error and the exact file and line number where it happened. Handing this object over to the runtime system is called throwing an exception. Normal forward progress is instantly paused. The runtime system then searches backward. It checks the function where the error occurred, then the function that called it, moving down the entire hierarchy of running methods. This is known as the call stack. If it reaches the bottom without finding instructions on how to handle the error, the result is a hard crash. Visualizing this automatic throw and search mechanism is required if we want to step in and intercept the crash. We don't have to wait for Python to automatically fail. We can proactively trigger these alarms ourselves. By using the raise statement, a programmer can forcefully throw an exception whenever a specific developer-defined condition is met in the logic. The raise keyword acts like a roadblock. Once it triggers, it immediately forces the program to jump out of its current block of code, stopping bad data in its tracks before it can corrupt later steps. Similarly, we can use the assert statement. This acts as a strict gatekeeper, testing whether a specific expression is true or false before allowing a function to proceed. If that expression evaluates to false, Python instantly generates an assertion error. By deploying tools like raise and assert, programmers draw lines in the sand. Unpredictable user inputs and edge cases are transformed into controlled, anticipated events. So once an exception is thrown, either automatically or by our own command, how do we catch it before it destroys the call stack? We use the ultimate architectural safety net, the try except block. Developers take suspicious lines of code, where a calculation might fail, and place them inside a try block. If an exception triggers inside this safe zone, normal execution stops. Instead of crashing, the flow is instantly rerouted to an adjacent except block. Control jumps to the except clause, officially catching the exception. Here, a backup plan executes, like logging error details or displaying friendly instructions. Once resolved, the program smoothly continues executing the rest of the script, as if the threat never existed. This brings us back to Stroustrup's philosophy of clean code. This try-except architecture successfully separates our primary logic from our messy error correction mechanisms. Anticipating and catching exceptions separates brittle scripts from robust professional applications. By building these safety nets, you ensure that when the real world inevitably breaks the rules, your code is ready to catch the fall.